Hello everyone and welcome back. So today we'll be talking about what exactly the centrifugal force is, and I'll also talk about some of the misconceptions that surround it. Especially the fact that it doesn't even exist. Which is truly false just because of the fact that there are several devices that are based on the principle of the centrifugal force, such as the centrifuge, which basically spins tubes filled with fluids in order to separate the various components present within it, which is used for blood analysis and stuff like that. So, to begin that, let's consider a very simple situation. We have an inertial reference frame. Now, an inertial reference frame is simply one which is not accelerating and which is not rotating. So this is your inertial reference frame that is not doing anything. And in this reference frame, you have a car that is moving in a circular track. So this is your circular track, and which really doesn't have a very well-made circle, which is which has a car that is moving in it in a circle like this. So at time t is equal to 0, that is at the start, it is at this point right here, and after some time t, you could say, it is at this point over here, and it has basically covered an arc of a circle. So we know for a fact that it is moving in a circle, and that since it is moving in a circle, there needs to be some force that is always directed towards the center, which we call the centripetal force. Now, the centripetal force in itself isn't a force of nature. That is, other forces of nature, such as the gravitational force, electrostatic force, these forces need to resolve in such a manner so that there is a force towards the center in order for there to be a circular motion, and this force is what we call centripetal force. Now, in our case, the force that serves as the centripetal force is basically the friction between the car's tires and the ground. That is the static friction that is present between them that allows there to be circular motion. And so we simply say that, suppose if I use the small f to denote the friction force, we can say that F is equal to MAC. That is, if we were to use vector notation, and AC stands for the centripetal acceleration. This is our equation of motion, everything's good, and we don't need to make any modifications. Which leads people to think, well, this is circular motion, then why is the centrifugal force acting? Where is the centrifugal force? Which of course leads to people thinking that, well, there should then be no centrifugal force. And that's where they're wrong, because centrifugal forces appear only in non-inertial frames of reference. There is frames of reference that are either accelerating or rotating, and centrifugal forces appear exclusively only in frames of reference that are in fact rotating. So what we will do now is analyze the exact same situation, but from a frame of reference that is rotating with the same angular velocity omega that the car is sort of going around the track with. So what I'll do now is just erase this whole thing that we had built over here, and I will then create another reference frame. But keep in mind that this frame of reference over here that we've created over here is rotating anti-clockwise with an angular velocity omega. And so what happens is that at time t is equal to 0, again we have our car over here, and we have our circular path over here, which is again not really circular. But after time t, we find that the car will remain at the same point. This is because in this frame of reference, there is no relative motion between the car and the frame of reference, so that the car will always remain at this particular point at all times as long as this circular motion is sustained, which basically means that the car is at rest in this frame of reference. But we know for a fact that the car is actually rotating in a circular track, it is moving along a circular track, so that there must be some frictional force acting. This is true regardless of the frame of reference that we use, because we know that the car is in motion, we know that it is rotating around the circular track, so there must be some friction. This is an undeniable fact of nature basically. It's just that since we are using a different reference frame, we feel that the car is at rest in this particular reference frame. Just as things stand at the moment, we have only one force acting. So keeping this in mind, let's try and write an equation of motion in this reference frame, right? So to write an equation of motion, we will need Uh, and when I say equation motion, I mean we'll try and apply the second law, Newton's second law of motion in this frame of reference. So we can write F is equal to m second derivative of the position with respect to time in this manner. So which implies, and since there's no circular motion, we can't really write in this frame of reference, there's no circular motion, so we can't introduce a centripetal acceleration to explain the fact that this is some form of rotation. In this frame of reference, there's no rotation, this is simply a force that is directed to the center. So what is expected to happen is that this body will then move towards the center like this, and will then reach the origin, at which point we can expect the force to stop. So, but this is clearly what is not happening. We observe that the body over here is at rest. And so, to sort of try and understand what this would look like in the frame of reference in which everything is at rest, that is the inertial frame of reference, we have, let me just draw this up in the corner over here. The motion will somewhat look like this, I suppose. That is, the car will sort of move like this, if the equation of motion that we have written over here is correct. But this is clearly not correct, because this is not what happens. We observe that in this frame of reference, the car moves in a circular path like this, and in this frame of reference, it always just stays at this point. So what is happening? In order to resolve this problem, we have to introduce the idea of a centrifugal force. To resolve this problem, we introduce a correction term, you could say, which is the centrifugal force. And so what we instead write over here is, we modify the equation of motion to instead read F, that is the frictional force in this case, minus m omega square r, you could say, with r is the radial vector, is equal to m d2r dv square. And this is our modified equation of motion. And in our case, in this particular scenario, it will be so such that F is equal to m omega square r, such that this whole thing over here is basically 0, such that this is 0, and that the body over here is at rest. So this is where the notion of the centrifugal force actually comes from, and that this is clearly not a fictitious force. But then again, I mean, I've said that this was introduced as a correction term, basically. So I mean, that might seem like this is just some idea, and that it really doesn't actually exist in reality. To show why this is not the case, let's consider a real life scenario, one that all of us are really quite familiar with, right? So let's consider us sitting in a car, right? So this is a rectangular box, which is actually supposed to depict the person, and this can be sort of thought as a car seat, alright? This is the car seat, this is the person, and we have a pivot over here, which basically denotes the fact that the car is currently rotating in a turn, right? So it's sort of moving like this. So what we have all noticed is that whenever we're sitting in a car that is turning, we sort of feel a sway to the right? That is, we would expect our upper body to move in this direction. Now what I will do over here is analyze this situation from both frames of reference. That is, one frame, the frame of reference that is inertial, in which that is at rest, in which the car is in fact going around this turn, that is, it is turning, and another reference frame in which it is at rest, and which I will invoke the idea of a centrifugal force. So in the first example in which it is at rest, in which this is, I mean, in the inertial frame of reference, you know that the car will sort of follow a circular arc, so it will be sort of like this, but our body will tend to go in this direction, because the force of the centripetal force, that is actually the frictional force of our seats, that is, you could consider that to be a frictional force between the seat and your body, which actually allows you to go in a circular path, exists only on the bottom part of your body. It doesn't actually act on the upper body. So what happens is that this upper body effectively has no force acting on it, such that it continues to follow the same path, because since f is equal to 0, there is no change to its motion, and it continues along with the velocity in this direction, that is, in a straight path. But the car is actually moving along the arc of a circle, right? It can be thought to move leftward. So with respect to the car, what you actually observe is that your upper body will be moving towards the right because the car is moving towards the left. You could think that in the reference frame of the car, you're actually moving towards the right. So which you effectively feel as the sway towards the right whenever you're traveling in a car. So in order to stay on the circular trajectory of the car, your upper body needs to exert some muscular force towards the right, basically in order to straighten yourself so that you follow the circular trajectory of the car. So let's just call this FM or something, for M for muscular. But then again, you might be thinking, well, we don't need to use this idea of the centrifugal force here. And you're perfectly right, because this is an inertial frame of reference, so there is no space to even bring the idea of the centrifugal force. So instead, we will analyze the same thing, but from an inertial frame of reference, right? Now, I mean, from a non-inertial frame of reference. And this non-inertial frame of reference is the one in which the reference frame is moving with the same angular velocity as the car, so that the car is effectively at rest. It is not going anywhere at all. It's just sitting there. In this case, the frictional force will still act because remember that regardless of whether we use the inertial or non-inertial frame of reference, the car is still going along the circular track, and hence the frictional force needs to act between the seat and your body in order to execute that circular motion. And since we are in a non-inertial frame of reference, there will also be a corresponding centrifugal force that will act along this direction. But the centrifugal force does not depend on point of contact. Remember that this is an extended body, it's not a point mass. So while there is no frictional force acting on your upper body, since it is not in contact with the seat, the centrifugal force will still act because of the reference frame. So that there is in fact a rightward force on your body that is not held back by the friction. So you do experience this force, and so you need to correspondingly apply a a muscular force, FM, in order to sort of bring your body, straighten your body, and in order to ensure that it follows the circular path. So the centrifugal force only appears basically in this non-inertial frame of reference, and it is in fact a very real thing. It is just that when we use an inertial frame of reference, we don't need to invoke the idea of centrifugal force, but its effects are felt nonetheless. It's basically using different ideas to explain the same phenomenon but in different frames of reference. And this practice in general is very useful for, well, any physicist, because being able to explain the same scenario using different reference frames is actually a very important ability. In fact, it was this idea that actually led to the formation of special theory of relativity. There is this principle that Einstein sort of used as the backbones of the special theory of relativity. So being able to use different reference frames accurately is a really useful ability, I believe. So I think this will be it for this video. In the next video, I'll be looking at how these different non-inertial forces actually arise mathematically. And in this video, I have only covered the centrifugal force, but there is also the Coriolis force and Euler force, which also appear in non-inertial frames. So I will be deriving them mathematically and little less intuitively, basically. So see you there, I guess.